and Bhakti Devi. Oh, Guru Bhakti Dasi and Bhakti Janaka. Not here. Not here yet. Okay.
We're not looking at that.
Okay. So, let me put down extra names. So I can put down the names. Handouts, I was told we were supposed to have such things. So I produced some. This is an outline of the lectures I propose to give with some recommended reading. These are merely recommendations. Actually, I realized after I produced this outline it's really more appropriate for a semester course. So I don't think I'll probably be able to cover all the points covered in the outline. But it gives an idea of some of the material that can be presented. So I'll let you have these around. Also, I have a couple of articles to read which will be relevant to some of the things I'm going to be talking about in the course of these lectures. The first article is a Xerox of an essay by Ernan McMullen that appeared in the book Synthesis of Science and Religion, which is the conference book for that Bombay conference put on by the Bhakti Purana Institute. This article is interesting because it shows the conclusions that will be reached by a person who wants to believe in God if he accepts the fundamental assumptions of modern science. This Ernan McMullen is a Catholic priest, so it can be assumed that he has some interest in believing in God. But the conclusions that he comes to are essentially atheistic at best. Although you can see that he doesn't really feel comfortable with those conclusions. Still, that's what he comes up with. So we'll be discussing the full issue. So it's interesting to see the conclusions this person has arrived at. Also, this is remarkably thick. This is a Xerox of an article I wrote, also presented at that conference in Bombay, called God and the Laws of Physics, which I will be discussing the subject matter of this article in a lecture on physics, which I've scheduled here as lecture number 4. So you could peruse this. You don't necessarily have to read the whole thing, but if you just read it over, it will give you some idea of what I'm going to be discussing. So I'll begin by giving a introduction to this series of lectures. The points that I'm making in the introduction are included here under lecture 0, number 0. This is what you might call Kakijya, or a solemn declaration of purpose. The basic idea is to describe the motivation for discussing science in relation to Krishna consciousness. Of course, as you all know, Srila Prabhupada had a lot to say about the subject of science and Krishna consciousness. Specifically, in many different conversations, morning walk conversations, evening conversations, and so forth, he explained that modern science is presenting a great impediment to the acceptance of spiritual knowledge by the people in general throughout the world, in the Western countries and also in India and indeed everywhere in the world today. And this is based to a very large extent on essentially speculative scientific theories. So he objected strongly to these theories, which he said were misleading people very gravely. And he wanted some of his disciples to who have some scientific and academic background to show that these theories are incorrect and present the conclusions of Krishna consciousness. He singled out one particular issue that's of importance in this regard, namely the question of what is life and what is the origin of life. This is a key issue because Krishna consciousness is very much life-centered. According to the philosophy of Krishna consciousness, the absolute source of everything is the supreme living being. So in that case, life, in that sense, life is the source of everything, including matter. In contrast to that, the predominant viewpoint of modern science is that matter is the ultimate reality, and everything is emerging from matter. Life is merely a byproduct of matter that arises under certain very particular circumstances, on a particular planet circling a particular star. So, according to this idea, life is very much secondary. So there's a profound conflict in basic worldview between modern science and Krishna consciousness. So I've made a number of points here that are significant because they come up in preaching endeavors involving science and Krishna consciousness. I first mentioned here the myth that there is no conflict between religion and science. You'll very often hear this if you speak about science in the universities. After the reading recommendations, these points are outlined. So, very often one will be told that many of the greatest scientists are very spiritual persons, and they see no conflict between religion and science. In fact, religion and science involve completely different areas of discourse, which don't even intersect. So there's no possible conflict there. This is very often stated. So the actual situation is that there is indeed no conflict between impersonal philosophy in its various forms and modern science. Mayavadi philosophy, or various Western forms of impersonal philosophy, are very compatible with science. It's easy to add the impersonal Brahman to any given scientific theory that you have. It's just like adding 0 to a number and getting the same number. There's no contradiction involved. You don't have to change anything. So many scientists have been impersonalists. For example, Einstein said quite a bit about religion, belief in God, and so forth. But his God was the God of Spinoza, which is completely impersonal in character. So there is, however, a very strong conflict between the religion expounded in the Srimad Bhagavatam and modern science. The reason for that is that the Bhagavatam takes the material world seriously as a creation which is produced by a supreme person, Krishna, through the manipulation of his energies. A great deal of the early portion of the Bhagavatam is devoted to explaining the process of creation and the universal form of the Lord, whereby the Lord manifests all the different aspects of the cosmos through his own potencies. Thus, the various aspects of Krishna are reflected in the universe. The basic idea of the Vedic literature is that all the different qualities, forms, characteristics, and so forth of the material universe are there because they are originally in the Supreme Person, and they are manifested through the conscious creative arrangements of the Supreme Personality. So therefore, the Srimad Bhagavatam has a great deal to say about the universe, and what it says is very much different from many important things that are stated in modern science. There's another point that I make here. I point out that the conflict between Krishna consciousness, or indeed personal forms of religion in general, and modern science, is not really to be thought of as a conflict between persons. Sometimes people will criticize those who would like to address the conflict between science and religion by saying that they are engaging in a kind of quarrel. That this quarrel is pitting religionists against scientists. But actually that is not the really significant conflict. The conflict here is a conflict of ideas, and it occurs within the minds of individuals. In fact, it even occurs within the minds of devotees. many of whom have done it because of what they understand concerning modern science. So, in view of this basic conflict, the program that we have in preaching involving science and Krishna consciousness is essentially devoted to building a bridge of understanding between the knowledge that we have from modern science and the knowledge that is there in the Srimad Bhagavatam. People today will tend to think that the Bhagavatam is mythology, that it is full of all kinds of stories which have no basis in reality. Actually, Bhaktivinoda Thakur was addressing this point in the Bhagavad, an essay that he wrote. He said it seemed that the Bhagavatam had no place in the 20th century. This was how the Bhagavatam looked to an educated young man who had gone through the British school system in India in the time of Bhaktivinoda Thakur. And that's even more true today. But the basic premise of Krishna consciousness is that the Bhagavatam is describing the universe as it is in all respects. Srila Prabhupada has pointed out that Vyasadeva had no business putting imaginary stories in his literatures. And in fact, it is not possible to separate the Bhagavatam into, say, two portions, one of which we could call mythology and the other part description of spiritual reality, and to try and draw a line between them. If you try to draw such a line, you'll find that inevitably you have to shift the line either to include everything in the Bhagavatam, in which case you give up Krishna consciousness as being simply myth, or you have to shift it to the point that everything in the Bhagavatam is accepted as it being actually real. So the fundamental premise of Krishna consciousness is that the Bhagavatam is describing reality, but in contrast to that, modern science presents a very different picture of reality. So the basic problem is to examine modern science and Krishna consciousness and see if we can understand which is right and why one should accept the viewpoint of the Srimad Bhagavatam as being correct. Now, inevitably, this involves a fair amount of what the scientists themselves call demolition work. I picked up this term at the British Museum. I went there to see one scientist there who, actually I came there to see a very old fossil skeleton that they supposedly had hidden down in their basement. And this scientist, it turns out, had a whole file of creationist literature. He was very much up to date on the creationists. And he said, well, we farm out these different creationist documents to different people to do demolition jobs on them. So the British Museum is very much aware of their need to establish their worldview as opposed to the viewpoint of the creationists. They see it as an ongoing battle, which requires demolition work. So inevitably, in addressing the conflict between modern science and Krishna consciousness, a certain amount of demolition work is required. So that brings us to the subject of this first lecture, which deals with the theory of evolution. Actually, the first two lectures deal with evolution in different aspects. And since I've arranged here for 5 lectures and we have 7 days, I may carry this over to 3 days on the topic of evolution. So I'll begin by giving a little bit of a history of the theory of evolution. Basically, this is a product of thinking that has taken place over the last 200 years, roughly speaking. Of course, it's been pointed out that there were thinkers among the ancient Greeks who had evolutionary ideas and so on. But in modern Western science, the theory of evolution can be traced back primarily to the 19th century, although there are precursors in the 18th century. Prior to this time, practically everyone in Europe had a theistic conception of the origin of living species. In Christian thinking, there were various somewhat vaguely conceived ideas of the ultimate nature of life. There was an idea of the soul, which wasn't too well defined, but it was universally agreed that living organisms, both human and animal and plant and so forth, were all created by God. The general conception was that they were created in 7 days, according to as given in the story of Genesis. So this idea of creation was there. The whole viewpoint was quite different from what we have today. One expression of the viewpoint that prevailed at that time is the idea of the universe as a cosmic organism. This idea is essentially Greek in nature, as many aspects of Christian thought were. The idea was that the universe can be thought of essentially as an organism, as a living thing with various inherent qualities and properties which are ultimately inconceivable to the human mind. The idea then was that life is really the basis of the universe, and the different specific forms of life that we see are natural expressions of this basic life principle. So, in the beginning of what has been called the scientific revolution, this idea was replaced by a different concept, namely the concept of the universe as a clock, or a machine. Clocks became very popular around in the 1300s in Europe, and gradually the philosophical idea of the universe as a mechanism made of interacting parts became more and more prominent. So I'm going to say quite a bit about that in the lecture on physics. Here what I'll do is stick more closely to the developments in the theory of evolution. So in Europe there were some early evolutionists, including a fellow named Buffon in France, and also Lamarck, who was also French. The early theories of evolution did not become very popular among scientists, and the main reason for this was that the early evolutionary theories were essentially mystical in nature. They still were adhering to this idea of the universe as some kind of organism, the idea that there's some kind of mysterious, incomprehensible, irreducible life principle that is activating nature. So the evolutionists, early evolutionists in Europe, proposed that this principle works by gradually urging life forms along through different transformations, starting with some very primitive organism and gradually becoming more and more advanced. But the process was essentially of a mystical character. There was an inherent desire within organisms to develop higher capacities, and as a result of this they began to manifest limbs, their brains grew, they crawled out onto the land from the water, and they acquired wings and began to fly through the air, and so on and so forth. So these ideas were not accepted by scientists. The reason for this primarily is that these conceptions did not fit into the mechanistic paradigm of science. The basic worldview of modern science sees everything as mechanical, and these ideas were mystical. So the development that really established the theory of evolution in the scientific world was Darwin's theory. Now, Darwin's own grandfather, Erasmus Darwin, had formulated the theory of evolution. And this was, once again, basically of a mystical nature and not accepted. But what Darwin did was propose a mechanical explanation to account for evolutionary change. Essentially, his idea was this. Living organisms, first of all, are just machines. Darwin threw out all ideas which would suggest that there is anything more to a living entity than simply mechanism. For example, he threw out the idea of the mind as being some kind of non-physical entity. He threw out the idea of a life force as being something separate from the principles of physics and chemistry. All this can be seen in his notebooks, for example. So he took the idea that the living entity is a mechanism. And living entities, organisms, can undergo variation. They reproduce by some process of heredity, which in Darwin's day was not at all understood. He actually knew nothing of genetics. He was a contemporary of Mendel, who was the founder of genetic theory, but he never communicated with Mendel. And in those days, Mendel's theory was completely unknown. So Still, Darwin was convinced that however heredity works, it's mechanical. It's something like writing down a statement in a book and then making a copy of that book, and so on. And he observed that there's variation among living organisms. They never come out exactly the same. So he proposed that this is due to some kind of copying error. That as you keep copying the book, the hereditary instructions over and over again, changes arise. Now, often it is said that these changes are random, and one has to understand what this word really meant to Darwin. His idea was that the changes that occur in organisms are random in the sense that they have nothing to do with the evolution of those organisms. They have some cause, undoubtedly, but the cause is totally irrelevant to the process of evolution. It's merely happenstance. It's as though somebody's walking along and a brick happens to fall off the roof of the building and hit him. There's a cause behind that, namely perhaps an accumulation of water behind the brick just made it fall at that time, something. So there are causes, but they have nothing to do with, say, the errand that that man was on. So these variations occur. So then Darwin introduced his principle of natural selection. His idea was that due to the circumstances in which the organisms are living, certain physical characteristics will be more favorable than others. For example, if you're dealing with horses, one horse may have longer legs than another, and because of that it will be able to run faster, perhaps. So that organism will be better equipped in the struggle for survival. Darwin was a student of the work of a fellow named Malthus, who explained that crop population tends to expand exponentially, but resources on the earth are limited. Therefore, inevitably there must be conflict. There must be pressure between different organisms. So his idea was that there's a continual struggle in nature, and an organism that is better adapted to life in particular circumstances will prevail in the struggle and have more offspring. Ultimately, Darwin's principle of natural selection is based on the idea of differential reproduction. That is, the organism is superior, which leaves more offspring, which can in turn leave more offspring, and so forth. So his idea was that variation and selection taken together are sufficient to account for all the life forms that we see, starting with some hypothetical primitive ancestor. He wanted to start, say, with a single-celled organism living in some primordial pond somewhere. And his idea was that just variation and selection alone, which are entirely mechanical processes, would result in everything, from oak trees to human beings. So that theory has become accepted throughout the world of modern science. Today, it is taught in all universities. Practically speaking, there are no reputed scientists who will come out in public and say that they don't accept this theory. So it's very interesting that this theory has prevailed to the extent that it has. So what I'm going to do, and already I've spoken nearly for half an hour, I made it to this video that I'm going to show tomorrow in that case. But that's all right, because we do have 7 whole days. So what I'm going to do is discuss some of the arguments which are put forward regarding this theory of evolution. Basically, the tactic of the evolutionists is to place the burden of proof on anyone who would like to challenge the theory. Now, here we're speaking of the theory of evolution. Discussions of evolution can be divided into 2 very broad categories. One is the question of empirical support of evolution in the fossil record, and the other is the discussion of the theoretical mechanism by which evolution is supposed to occur. Actually, the theoretical mechanism is very important because it was due to the fact that Darwin proposed a mechanistic theory that his theory of evolution was actually accepted. The idea of evolution itself, as I said, had already been quite common. So what I'm going to be discussing initially is the theory, the theoretical considerations. And we'll discuss the fossil record later on. We have quite a bit of material on that also. So the basic argument which is made to defend the theory of evolution is based on, as I was saying, putting the burden of proof on anyone who would like to challenge. Essentially, in the whole domain of evolutionary study, there is very little solid evidence that actually proves evolution. I should eliminate a number of common misconceptions. Sometimes someone will say, well, we actually see evolution in action. For example, there's the story of the peppered moth. And it is claimed that in the case of the peppered moth, we can actually see evolution taking place. So this is proof. Evolution simply must be accepted. So I'll briefly recount that story. There's a kind of moth that lives in England, and which has two color forms that are known historically. In one, it has gray mottled wings, and in the other, it has black wings. So it used to be that throughout the sort of northern region of England where this moth lives, the trees were covered with a great deal of lichen, which has a sort of grayish color. So these moths, which were gray, blended in very nicely with the lichen, so that if a moth lit on the tree trunk, you couldn't tell where the moth began and the trunk left off. It was practically invisible. Now, the black type of moth, though, stood out very vividly against these gray tree trunks. So the tendency was that birds would eat the black moths, and they would leave the gray ones. Well, with the Industrial Revolution, the tree trunks were all covered with soot, and they became black. So what happened was that now the black moths blended nicely against the tree trunks, and the gray moths stood out. And it was observed over the course of about 50 years or so that the relative proportion in the moth population of gray to black form changed very dramatically. Now the gray form became extremely rare, and the black form was very common, whereas it used to be exactly the other way around. So it is argued that, well, here we see natural selection in action. There's variation, black versus gray, and there's natural selection provided by the birds. So this is taken as proof. And then a further point is that in recent years there have been some air pollution control efforts in these northern English cities, and many of the trees have gone back to their gray form. And now it's been observed that the moth populations are also going back. The gray form is becoming more prominent again compared to the black form. So does this prove evolution by natural selection? Well, the answer here, simply enough, is that there's no reason at all to deny that natural selection takes place. Here we have an example, and this is all well and good. But the premise of the theory of evolution is that variation and natural selection are sufficient to account for all biological form. So here we have natural selection distinguishing between two types of wing color in these moths. But one might ask, what about the wings of the moths, for example? How did they arise? What about all the different complex features of these organisms? Are we justified in extrapolating from wing color to the many different complex features that you find in these moths? That would be a tremendous leap. So what we actually find is that there are various simple examples similar to this involving natural selection, including studies involving fruit flies in captivity, many different considerations. But these really beg the question. The scientists themselves would say that at most these demonstrate what you could call microevolution, the modification of some very, one might almost say, insignificant feature of an organism. But there's the question of macroevolution, or the development of significant features. In the case of the moths, the development of the power to fly, for example. So one is naturally interested in macroevolution. And basically, macroevolution is supported by hand-waving arguments. I should, just to anticipate some things we'll say about the fossil record, I should point out that evolution is not really supported by the fossil record. And in fact, this has been indirectly admitted in recent years by evolutionists themselves. In fact, the history behind this is interesting. For years and years, Christian creationists would give debates in which they would point to standard textbooks of evolution. And they would point to genealogical trees place, and these are drawn in the form of a tree with different branches, all leading up to presently existing forms. So these creationists would point out that in these trees there are a lot of dotted lines. There are solid black lines corresponding to forms that either actually exist or are actually known from the fossil record. And then dotted lines are filled in, which are entirely hypothetical, based on the idea of what must have happened if evolution is true. But in these diagrams, you'll find that if you erase all of the dotted lines, you're left with a series of separate little short segments, which are disconnected. So the whole idea of an evolutionary tree is completely hypothetical. So creationists were pointing this out. So finally, scientists began to respond to this with something known as the theory of punctuated equilibrium. Now, according to the theory of punctuated equilibrium, evolution takes place. In fact, it even takes place gradually. But it does this in a unique way. There are two things called stasis and punctuation. The idea of stasis is that a given species remains completely fixed in form for the overwhelming part of its existence on the Earth. It doesn't change. But at a certain point in time, a small group of organisms may wander off from the main population into some remote region, and there they will undergo very rapid evolutionary change and perhaps develop a superior form. Then this superior form will migrate back into the original homeland and take over because of its superiority. The result is that in the geological record, you'll see an abrupt replacement of one form by another, with no sign of the gradual transition that occurred. So that is one way that the evolutionists have responded to the challenge that was posed by these creationists. Evolution occurs, but because of this punctuational pattern, it's effectively invisible. Then there's another aspect that they have invoked, and that is the idea that evolution is like a bush rather than like a ladder. We recently attended a lecture by Stephen Jay Gould at San Diego State University, in which he expounded this concept. It was interesting. Over 1,000 people attended this lecture, and they had to close the doors of the lecture hall to keep more people from coming in because they were out of seats. So Gould was saying evolution is like a bush and not like a ladder. So here's what he meant by that. The traditional idea of evolution is shown, for example, by the sequence which you can find in the New York Museum of Natural History, showing the evolution of the horse from a creature called Eohippus. Eohippus is said to have been a small fox-like creature. And you'll see in the exhibit and in many textbooks a series of increasingly horse-like forms going from this little Eohippus on up to the modern horse, almost in a continuous sequence. So evolutionists now admit that this picture is very misleading. In fact, it's completely false. The idea behind it is even false, according to Stephen Jay Gould. The idea behind it is that you have a unidirectional progression from one form to another, that there's direction in the process of evolution. But the picture that Gould would like to substitute for this is that evolution is instead like a bush. So imagine a bush that has a trunk that bifurcates again and again into branches and more branches, and that these branches twist and turn in a very tangled way. So he's saying the evolutionary developments are really
comparable to this. The practical implication of that is the following. If evolution was like a unidirectional ladder, then if you could pick a few samples of fossil forms from that progression, let's say 10 or so, you would expect that the basic evolutionary picture would become quite clear, because you're just sampling a few points on a straight line, and you should very easily see how they line up. But imagine if you take just a few samples from a very complicated bush. Then one sample is going to come from one branch, and another one will come from some other branch, and so on. So once you've taken a few samples, you won't see any pattern at all. You'd have to take hundreds and thousands of samples in order to begin to outline the interconnections in this bush. But unfortunately, the fossil record is extremely incomplete, and one doesn't have all these hundreds and thousands of forms. So therefore, again, there's no evidence for the evolutionary interconnections. They're just not visible, and you shouldn't expect them to be visible. This was the basic message. Yet, evolution is an incontestable fact. This was also his message. So, what I'll turn to now then is the kind of argumentation that you see, and we'll turn on this overhead projector here. This is the eye. So, we'll start with an example given by Charles Darwin that really epitomizes the whole situation. Darwin was confronted with the question of how could the eye evolve. So, the eye in a human being, what to speak of a bird like an eagle, is a very remarkable instrument. There's the arrangement of the lens, which can focus light on the retina. It can focus light very sharply. Then in the retina, there's a very elaborate arrangement of cells, light-sensitive cells, that are hooked together. Now we know that they're hooked together into pattern detectors and respond selectively to lines and circles and so on and so forth. So it's a very remarkable high-precision instrument, certainly superior to this video camera back here in many different ways. So the question is, could the Darwinian mechanism of evolution account for this? So Darwin made the statement at one point that if my theory cannot account for something like this by a series of gradual steps, intermediate forms, starting from some primitive initial form, then my theory will absolutely break down. So he said, though, but I can conceive of such a series of intermediates. And he proceeded to outline in words what this series of intermediates would be. Darwin's proposal was that all you have to do is start with a light-sensitive spot on some simple organism. For example, there's a creature called the euglena, which is a single-celled organism, which has a light-sensitive spot. It's just a little region of pigment, and apparently it's photosensitive. And when light strikes that, the organism can recognize this and then turn one way or the other, as it wishes to do. So Darwin said, well, let's start with that. Then you can go through a series of intermediates all the way to the eye. For example, you can say, initially, let this light-sensitive spot get a little bit bigger, because after all, if it's bigger, then it can catch more light, so that's better, you might say. That organism will survive and struggle for existence. And as it gets bigger, you can imagine it begins to dent in, because this will help protect it, perhaps, from being struck by something. Once it begins to dent in, now there's the possibility that a shadow will be cast if the light comes in obliquely. And if nerve connections then develop to some kind of evolving brain within the organism, then the possibility of detecting direction of light is there, which is a whole new sensory capacity for the organism. So therefore, that's better. Now, if we can carry this further, the thing dents in more and more, and you can imagine the upper rim of this light-sensitive pit to close in, and once it closes in enough, it begins to form a pinhole pattern. So the possibility of forming images is now there. And if the nervous system also is evolving in parallel with this, so that it can take advantage of these images, then the organism can begin to see forms. So that gives it a great advantage. And then you can imagine that some layer of tissue will grow over the pinhole, initially for protection. That would give an advantage, so that, it frees it from danger of things getting into the hollow of the eye and so forth. But then, of course, this layer should be transparent, as very thin layers of skin are. And if it begins to bulge just by a mutation or variation, then you can have the first lens. And by gradually perfecting this lens, you finally come to a camera-like eye, such as we have. And in this way, gradually you wind up with the human eye, or even the eye of an eagle. So Darwin outlined this series of steps. And he thought this was conclusive. This was sufficient to prove this case. And many other people have accepted this line of reasoning to this very day. Now you might say, well, wait a minute. Would it really work that way? First of all, do we have examples of these different intermediate forms? Now, if you look at, of course, fossil organisms, you won't find fossil eyes because they're soft. They're not preserved in fossils. But you can look at different existing species, and you'll find eyes of various types. Some of them are very primitive. For example, clams have little eyes along the rim of their shell, and so on. So you can try and put together a series of eyes that correspond to Darwin's sequence of intermediate forms. But if you do that, you will find, you will find that they're really quite different from one another. Each one has a radically different structural plan. In no way are they intermediates. They merely provide more mysteries to explain instead of providing an explanation of how the eye came about. So ultimately what it comes down to is the idea of accepting this argument of the evolutionists. And basically they will put the burden of proof on any person who would like to challenge this and say, well, show that you couldn't have a series of intermediates like this, which would lead up to the eye. If you can't show that it couldn't be, then you should accept the theory of evolution, because after all, evolution is the grand unifying principle of biology. We could not understand anything in modern biology without the theory of evolution. So, unless you can show something wrong with this, you should accept the theory. So, this is the kind of argument that is made. So, what I would like to do is take up their challenge and show why this won't work. So to do that, what we're going to do is discuss machines. And it's appropriate to do that because the evolutionists are saying essentially that life is a machine. So therefore it's legitimate to discuss machines. I will spend the rest of the time, I think, discussing this little picture, which first appeared actually in a Back to Godhead article that I wrote back in 1975. So what this picture symbolizes some points that are of some importance. So what we want to do here is consider the question of evolution as applied to machines. Now, ultimately, we're going to talk about the machine of the body. And in fact, we're going to talk about molecular machinery of cells. But initially, we'll talk about a simpler kind of machinery, namely machines made of gear wheels, because everyone can understand those. So, what this picture symbolizes is a way of representing all possible machines of a given type. So, imagine a machine made of gear wheels, such as a watch, for example. You can imagine describing that machine in terms of many different numbers, representing different key measurements that you could make to describe the mechanism. For example, the radius of one of the wheels would be one of these numbers. So for each wheel, you'd have the radius of that wheel. Also, the position in space of the axle, the orientation of the axle, and so on. So you can imagine giving a long list of numbers. It may run many hundreds of numbers. And that list of numbers will define the given machine precisely. So that list of numbers can be thought of as a point in a multidimensional space. For example, you may know a plane, a two-dimensional space, can be defined by 2 points, namely x and y. And you can go to 3 dimensions and go to x, y, and z, which define a point in 3-dimensional space. So similarly, to describe various machines, made of gear wheels, let's say, you can describe them as points in a multidimensional space. So the reason that this is interesting is that you can then ask what points in this space correspond to working machines and what points correspond to machines that don't work. So by working or not working, we mean working or not working from the point of view of human users, that is, people who are going to utilize the machine. This corresponds to the idea of viability of an organism. The organism has to live in a given environment. So similarly, a machine, so to speak, lives in the environment of the human users who find it useful or not. So many machines corresponding to points in this space are not even physically possible. Because, for example, 2 gear wheels may overlap or something like that, which is not possible. So you could take a large region of this space and just eliminate that, because that corresponds to impossible machines. Then, of the space that remains, practically all of it is going to correspond to machines that are mere jumbles of gear wheels. They don't do anything. So that's what's portrayed here. Here, this ocean represents our space. It's being represented as a 2-dimensional surface, whereas it's really has many hundreds of dimensions. And the longer part corresponds to machines that are not viable. That's why we put these just random-looking collections of gear wheels here. Practically all of them are totally useless. The items correspond to machines that are viable, that perform some function. So the basic point that is to be made here is that in this total ocean of useless machines, the islands corresponding to useful machines will be very small. You can think of the Pacific Ocean with a few Polynesian islands in it. In fact, the islands will be even more sparse than that. And you can do mathematical calculations to show how sparse. So the height of a given island above the sea level corresponds to how good the machine is. Let's say this island corresponds to this particular machine, whatever it was. I think it is a bit block, actually. So if you move slightly in the space, that means you're changing certain features of the machine just slightly. And you can see in the case of a watch, imagine what happens if you make one gear wheel a little bit bigger. Well, if that's all you do, you probably ruin the watch. It simply won't work. That means if you change just slightly, you'll go right off the island into the ocean. These islands are actually extremely narrow, extremely tiny, and as well as being extremely scarce. And if you think of the watch again, if you enlarge one wheel, then maybe you could compensate by making another wheel a little bit smaller. But probably you'd have to make the 2 wheels that connect with that one wheel a bit smaller. But then they connect with those wheels, so you'd have to change them a little bit also. So if you make changes in practically all the wheels, which are coordinated in the sense that one change is related to another change, then the watch might still work, but perhaps it would keep a very bad time because of those changes. If you made the changes in a very precise way, then you might improve the timekeeping of the watch, assuming that initially it didn't keep very good time. So this is the nature of changes or variation as applied to machines. Now let's apply this to the idea of random mutations in nature. Suppose you were to make these changes in a machine in a random way. That is, you have your list of numbers. The list of numbers can correspond to the hereditary information for the given machine. Now in organisms, there's this DNA, which contains hereditary information. The idea is that the DNA code contains the total blueprint for that physical body. So the sequence of numbers corresponds to the blueprint for one of these machines. You can then imagine what happens if you randomly change some of these numbers. We've made the point that you change the machine in such a way that it will still be functional. If you change one number slightly in one way, another number has to be changed in a very precise way that corresponds to that. If you're just changing them at random, it's highly unlikely that that's going to happen. In other words, if you randomly zap the blueprint for this wristwatch, the chances that you're going to get an improved wristwatch are extremely small. In fact, you can do calculations and conclude that it's not going to happen in a million or a billion years, assuming that you make your changes at a certain rate. So that's an outline of a basic argument that can be made. So what we want to do is apply this, of course, not to wristwatches, but to organisms. So a lot has been learned about the machinery of organisms since Darwin's time. I should first of all make the point that even according to the Bhagavat Gita, the bodies, the gross physical bodies of living organisms are mechanical in nature. They're referred to as yantra rudani mayaya, as machines made of the material energy. And, of course, one might suggest that in Vedic times they didn't have very sophisticated ideas of machines. Someone will perhaps make that suggestion. But actually that's not true. I have some medieval secular Sanskrit literature. It's called the Samarangana Sutra Dara by someone named Bojadev. It's not spiritual, just secular literature. But it referred to robots. At least it can be said that the idea of robots was very much there in India many centuries ago. There are all kinds of descriptions of mechanical men that can walk around and do all kinds of things. So whether they built them or not, certainly there's no question that the idea was there of very sophisticated machines. So we're getting toward the end of our period. This is an example of a protein molecule. It's one of the molecules that appears in the cells of living organisms. So what I want to introduce now is some idea concerning the kind of mechanisms that are present in living organisms. As we know, cells in living organisms can do very remarkable things. For example, you eat some food, and the food is processed in a way that you don't understand at all. That is, the eaters don't usually spend too much time thinking about it. But somehow, all the different tissues and so forth are built up within the body based on the food that we eat. So it's a very remarkable process which involves molecules that are called enzymes. This is an example of such a molecule. Actually, this is cytochrome C, which is involved in electron transfer in mitochondria in cells. But the basic idea of an enzyme is this. An enzyme will cause a certain chemical reaction to occur millions of times faster than it would occur without the presence of that enzyme. And it will do this very selectively. It will have no effect at all on other chemical reactions. There'll just be one particular chemical reaction that it makes go very fast. And it does this by a rather remarkable mechanical feature, at least as far as scientists have been able to understand in their attempts at reconstructing these molecules. For example, one enzyme may break a particular organic molecule at a particular place. So what it does is it has form-fitting grasping elements, you might say, that grab a hold of that molecule in two different places. And then a special arrangement that severs the molecule at just the right place. And then it lets go of the two pieces that it's grabbed. So these enzymes are precision instruments. Many of them have a property of switching. They're not always active. A given enzyme will only perform its function if it is switched on by another molecule that connects with it. So there's a control system which turns the enzymes on and off. And this control system can be compared with a computer. In fact, it is far more sophisticated than any kind of computer that has yet been built by human beings. Today we're very proud of our computers. But the circuitry of a modern computer is nothing compared with a simple bacterial cell, such as the E. coli bacterium, which is the kind of bacterium that lives in your intestines, for example. And the cells of mammals, higher organisms, are even more complex. Just to give an idea of one of the things that happen, I happen to have another slide here. This shows one of the things that goes on in metabolism. This is a series of steps in the synthesis of an amino acid, which is kind of molecule important in the body. Each step is controlled by an enzyme. Each of these dark circles represents that enzyme. The enzyme takes you from one step to the other by performing a very specific chemical operation. What we have here is that when the end product of this series of reactions accumulates within the cell, then it acts on this enzyme back here and causes it to switch off, so that the manufacturing process stops back here. So as soon as the cell has as much as it needs with the end product, it stops producing the intermediate products automatically by the switching mechanism. And there are thousands and thousands, millions in fact, of similar switching mechanisms and so forth within the cell. So in many ways, it's comparable to an elaborate computer. So it is now 6:30, and I'm supposed to speak for an hour. I've sort of built up to the initial argument that I'm going to present concerning the theory of evolution. So I guess for now I will proceed to present that. And we have a video also that I would like to show. I'll just announce briefly what that is. This presents a lecture which I gave at a conference on the theory of evolution held in Budapest. This conference was held by professional scientists in this field to discuss the whole different ideas they have about evolution. So actually the presentation was well received. There was a fellow, John Maynard Smith, who was there, who is known as the Pope of Darwinism in England. And he actually incorporated some of the comments I made into his remarks, which he summed up the conference. So, however, certain other scientists there accused me of non-evolutionary thinking. So I'll be presenting that tomorrow. For now, are there any questions or comments on this